Hello, this is Dr. Hanaa Assil, and this is a final review on Unit 5. This is in the A2 Chemistry Edexcel. So let's take a look at the topics that we need to know for Unit 5. First, we need to talk about electrochemical cells, and you probably know by now that an electrochemical cell is made by connecting two half cells together. So if we have zinc and copper, for example, where do we have oxidation? Where do we have reduction? You should know that oxidation happens at the anode, which is the negative electrode, and reduction happens at the cathode, which is the positive electrode. So what happens in the anode is that the more reactive metal, which is zinc, for example, loses electrons, while at the cathode the less reactive gains electrons. The two half cells are connected by salt bridge, and you know that this salt bridge is usually a U-tube containing a saturated solution of potassium nitrate, and this allows the movement of ions between the two solutions. For each half cell, we need to determine its standard electrode potential. And you should know that the standard electrode potential is the potential of the half cell, which has a solution and an electrode. And this is in relationship or compared to the standard hydrogen electrode. These are obtained using solutions that have a concentration of 1 mole per decimeter cubed. It is measured at 298 Kelvin or 25 degrees Celsius, and at a pressure of 1 atmosphere, which is 100 kilopascal or 101 kilopascal. So all electrode potentials are measured in reference to the standard hydrogen electrode. The standard hydrogen electrode is basically a half cell containing hydrogen gas coming in at a pressure of 1 atmosphere and 298 Kelvin, a platinum wire, and a platinum electrode that is covered with finely divided iron, and this is dipped into dilute acid at a concentration of 1 mole per decimeter cubed. So what happens is the hydrogen gas is allowed to go in. It goes to the platinum electrode, and this platinum electrode is covered with a layer of what is called a finely divided platinum. The finely divided platinum actually acts as a catalyst. It allows equilibrium between the gas and the solution to be established quickly. It allows close contact of the hydrogen gas with the H+ ions in solution. And of course, we use platinum because it is inert. It does not take part in the reaction. So we need to know all of this. Now, the half equation is the H+ plus 2 electrons forming hydrogen gas, and the standard hydrogen electrode is given a standard electrode potential of 0 volts. So if we say state the value assigned to the electrode potential of the standard hydrogen electrode, of course that is 0. And if the question says explain why a reference electrode is needed in the first place to measure the electrode potentials, this is because remember that a potential difference requires a complete circuit with 2 electrodes. So in order to get the electrode potential of a half cell, you need to connect it to another half cell. What is the pressure of the hydrogen gas used in the standard hydrogen electrode? We said it is what? It is 1 atmosphere. Now, which of these is 1 atmosphere? You should know that 1 atmosphere is the same as 100 kilopascal or sometimes we say 101 kilopascal, and that is the same as 100,000 pascal. So in your data booklet, you're going to have this. This is the list of standard electrode potentials. They are all reduction potentials. So all of these are standard reduction potentials. They are arranged from reduction potentials that are more negative to the ones that are more positive. We said this is all in relationship to hydrogen electrode, which is given a value of 0. So in this list, the one on top are the ones that have electrode potentials, reduction potentials that are more negative. That means they are better reducing agents. Remember, the ones on top are the more reactive metals, which tend to lose electrons, not gain electrons. So they are better reducing agents and they tend to lose electrons. The ones at the bottom, as we go down, these have a more positive reduction potential. That means they are more easily reduced and they tend to gain electrons. So if we have a question like this, it says use these electrode potentials. Sometimes you're given the table in the question and sometimes you're told to refer to the data booklet. So this question had this table and the question was, which of these is the strongest oxidizing agent? It is arranged in the same order as the data booklet, from the negative reduction potentials to the more positive reduction potentials, and that means the one on top is a better reducing agent. We're being asked which one is the strongest oxidizing agent, so we're looking at the one at the bottom of that list. This is another question. It says standard electrode potentials can also be given an alternative name. The electrochemical series lists standard electrode potentials in order. Which of these is correct? Again, we said these are what we call standard reduction potentials. So they're from the better reducing to the more easily reduced. So it goes from the most negative to the most positive. This was a question that talked about an electrochemical cell that has a half cell made up of zinc and zinc chloride solution, and a second half cell made from a piece of metal which we don't know, so we're giving the letter G, and a solution of its chloride. The two half cells are connected and a current allowed to pass for some time, and they found that the zinc electrode increased in mass by 1.635 grams. The metal G decreased in mass by 0.6075, and we're asked what is metal G. Well, okay, so the G decreased by a certain mass and the zinc electrode increased by a certain mass, so we can get the number of moles of zinc that reacted. So number of moles of zinc that reacted is the mass over the molecular mass of zinc, and this comes out to be this number of moles, and that means it would be the same number of moles that reacted in G, since it is both zinc chloride and GCl2, so it would be the number of moles of the G would be the same. I am given the change in mass, so I can calculate the MR. The MR comes to 24.3, and that means that I'm looking at magnesium. This was another question where we're given the hydrogen electrode half cell and another half cell. We're told that the other half cell has iron 3, iron 2, so iron 3 going to iron 2 plus. The measurement is made under standard conditions. Identify by name or formula the substances needed in the salt bridge the right-hand half cell to measure the standard electrode potential. We said if we have a salt bridge, the salt bridge contains a saturated solution of potassium nitrate. That's the usual one. Electrodes should be made of what? Now, if we have a half cell in which all we have is solution, so we have iron 3 plus and iron 2 plus, then the electrode is platinum. But if we have a solid somewhere in that half equation, then the solid is the electrode. So here all we have in my half cell is iron 2 plus and iron 3 plus solutions. So I need an electrode made of platinum. The solution should contain both iron 2 and iron 3, each with a concentration of 1 mole per decimeter cubed. We said the solutions have to be in concentration of 1 mole per decimeter cubed. So if we have this question, which electrode and solution would be used to measure the standard electrode potential of the manganese 3 plus to manganese 2 plus, again, this is a half cell that has only solution, so my electrode must be platinum. Now we need the half cell to have solutions of both manganese 3 plus and manganese 2 plus at concentrations of 1 mole per decimeter cubed each. The apparatus shown was used to measure the standard electrode potential for dichromate to chromium 3 plus. Which material should be used for each electrode? Again, the electrode 1 is the one in the standard hydrogen electrode, and you should know that the one in the standard hydrogen electrode, the electrode is platinum. Now, the second half cell is something that has, again, dichromate solution and chromium 3 plus solution. That means we don't have a solid in that half cell, so my electrode also must be platinum. Solution 1 is what? We said in the standard hydrogen electrode, solution 1 is what? It is 1 mole per decimeter cubed of a strong acid. So it has to be a strong acid, not ethanoic acid, and it has to be at 1 mole per decimeter cubed concentration. Then another kind of question would ask that we should draw a cell diagram. How do we draw a cell diagram, or how do we write out a cell diagram for a certain E cell? Well, we start on the left with the oxidation part and on the right with the reduction part. Now, where is the oxidation? Where is the reduction? The equation has iron 2 plus going to iron 3 plus. So that is the oxidation. So that has to be written on the left. These are a mixture of solutions. So the electrode must be platinum. So my answer is C or D. And then on the right, I should write the second half equation. What is happening? I have manganate plus 8H plus changing into manganese 2 plus 4 water. So that is what I should write in the cell diagram. Again, this is a mixture of solutions, so the platinum electrode has to be used. Again, if we say write the cell diagram for a half cell for these two reactions. So we want to produce chlorine. Again, if you look at the electrode potentials in the data booklet, if you need to invert the equation, you invert the sign of the E cell. So here we want to produce chlorine. So that second equation, instead of going from Cl2 to 2Cl minus, I want it to be something that produces chlorine. So these are my equations. This is what is happening. How am I going to write the cell diagram? Again, what is happening? Where is the oxidation? Where is the reduction? We have the chloride going to chlorine. That is the oxidation part, where chloride loses electrons and becomes chlorine. So that's the part that will be written on the left. this is a mixture of what? Chloride solution and chlorine gas. We don't have a solid in that half cell, so my electrode must be platinum. Now, platinum and then chloride going to chlorine, and then we put a double line to indicate the salt bridge, and then we write the reduction part on the right. What is happening? We have the dichromate plus 14H plus going to chromium 3 plus 7 water. You write it as it is from the equation. Again, this is a mixture of solutions, so my electrode on the other side also has to be platinum. Okay. Then, if we're required to calculate the total E cell, you should know that the total E cell is actually the total of the oxidation part plus the reduction part. And to know if a reaction is feasible, the overall E cell should be positive. So if we're asked whether it's feasible, we calculate the E cell. If it's positive, then it is feasible. So, for example, this question, the EMF of a cell is plus 0.57. The numerical values of the standard electrode potentials of the two half cells are 0.17 and 0.40, but we're not told whether it's plus or minus. What are the signs of the standard electrode potentials of the right hand half cell and the left hand half cell? So I want the total to be plus 0.57. So how can I make the total plus 0.57? Remember that the one on the right hand side is the right hand cell is oxidation, and we want the total E cell. The total E cell, we said it's E oxidation plus E reduction. So in this case, it is the E of the right hand minus E of the left hand half cell. And in order to have a total of plus 0.57, I should have the left hand cell negative, so it should be minus 0.17, and the right hand cell is positive. Sometimes the E cell is positive, so the reaction should be feasible, but actually it is too slow. In that case, we say that that is because the activation energy is too high. Remember that the E naught of a cell is proportional to the natural log of K, which is the equilibrium constant, and is proportional to the delta S total, which is the total change in entropy of the system. So if E naught of a cell is positive, then the delta S total also is positive. This question, for example, says sometimes the calculated value of E cell for a reaction shows it to be thermodynamically feasible, but in the laboratory no reaction occurs. Give two possible explanations for this. Of course, this could be because, first of all, the activation energy is very high, or the conditions of the reactions are not standard, so the temperature, for example, is not 298, or the concentration is not 1 mole per. So this question, for example, says the value of E cell for a reaction is positive. It can be deduced that what? If the E cell of a reaction is positive, well, the one we said first of all that the E naught is proportional to ln K. It's proportional to delta S total. And if the E is positive, then the delta S total must be positive. Total, not system or surroundings. For the reaction shown, we're given that the E cell is plus 0.89. Which statement can be deduced from this information only? So we said if the E cell is positive, what does that tell us? It tells us that the reactants are thermodynamically unstable with respect to the products. The E cell is positive. That means the reaction would occur. It's feasible. And that means that the reactants are unstable with respect to the products or the reactants would certainly change into products. Okay, we said the solution in the half cell should be 1 mole per decimeter cubed of each ion that we need. Now, if this question says what mass of iron 3 sulfate is present in 100 centimeter cubed of the solution used to measure the standard electrode potential of the cell. Remember, iron 3 sulfate, first of all, overall I want a concentration of 1 mole per decimeter cubed of the iron 3 plus. But in the iron 3 sulfate, 1 mole of the iron 3 sulfate gives 2 moles of iron 3 plus. So if we say the number of moles of iron 3 plus is the concentration times the volume, the concentration I want it to be 1 mole per decimeter cubed. The volume we're given is 100 centimeter cubed. That means 0.1 decimeter cubed. So the number of moles of the iron 3 plus in solution should be 0.1 mole. And the question is, that means how much iron 3 sulfate should I put? Well, if I want 0.1 mole of the iron 3 plus in the solution, then I need half of that number of moles of the iron 3 sulfate, because 1 mole of iron 3 sulfate gives twice the number of moles in the iron 3 plus. So the number of moles of the iron 3 sulfate I need is 0.05, and that means the mass that I need to put in the 100 centimeter cubed would be the number of moles times mR, which is about 20 grams. Remember, the idea is we need overall 1 mole per decimeter cubed of iron 3 plus ions. And each mole of iron 3 sulfate gives 2 moles of the iron 3 plus. So based on that, how much iron 3 sulfate should we use? This question says a student suggested that for standard conditions, solution A should be made by mixing equal volumes of 1 mole per decimeter cubed of iron 2 and 1 mole per decimeter cubed of iron 3 sulfate solutions. This is not correct. Why is this not correct? Because the iron 2 sulfate, if I use 1 mole per decimeter cubed of iron 2 sulfate solution, that means I have 1 mole per decimeter cubed of iron 2 ions. That's correct. But if I put in 1 mole per decimeter cubed of iron 3 sulfate solution, that means my concentration of iron 3 plus is twice of that. So actually, when I want to mix iron 2 sulfate and iron 3 sulfate in order to make the half cell, I need to put concentration of iron 2 sulfate 2 mole per decimeter cubed, so that the concentration of each iron is 1 mole. So I need to put 2 mole per decimeter cubed of iron 2 sulfate with 1 mole per decimeter cubed of iron 3 sulfate. In that case, the concentration of each of the ions, iron 2 and iron 3, would be 1 mole per decimeter cubed. The half cell for the iron 3 plus, iron 2 plus electrode system is prepared by mixing equal volumes of iron 2 sulfate and iron 3 sulfate. What concentrations of the original solution are needed to make the mixture to be standard? Again, pay attention. We want a half cell to have 1 mole per decimeter cubed of iron 2 ions and 1 mole per decimeter cubed of iron 3 plus ions. If I have the iron 2 plus, I should start with 2 moles. Then this will give 2 moles of iron 2 plus, so that when I mix equal volumes, that means I'm diluting it by half, then the concentration of iron 2 plus would be 1 mole. But the iron 3 sulfate, I should start with a solution that's 1 mole per decimeter cube, so that the concentration of the iron 2 plus is 2 moles. Then when I mix equal volumes, then each of them would be diluted by half. So the concentration of each of the ions would be 1 mole per decimeter cubed. This question wants to identify the compounds that are used to make solution B. In solution B, we want the manganate to manganese 2 plus. That was our solution B. So if I want to add solutions so that they are manganate and manganese 2 plus, which compounds should we use? Remember, we need soluble solutions. So usually we use potassium permanganate and something nitrate. So if I want manganese 2, then it is manganese 2 nitrate. So if we have a question like this in which we have the 2 reduction potentials and we are told which is the equation for the overall cell reaction. Well, looking at these, which one should be oxidation, which one should be reduction? Remember, the one that is less positive is more likely to be the one that loses electrons, not gains electrons. So the oxidation of silver solid to go to silver plus, and that means we need to invert that equation, and that means we need to invert the sign of the E note. Then we make sure the number of electrons are equal, cancel whatever is the same on both sides, and the overall equation would be this one. This question is about this reaction. The electrode potential for iron 3 plus, iron 2 plus is plus 0.77. And we're given the total for the E cell. What is the electrode potential for the titanium? Again, let's remember that when we're asked about this, we're supposed to give the reduction potential. What is required is reduction potentials. That's what we have in the data booklet. So what is happening? We have the iron 3 plus going to iron 2 plus, and that is given the E note that we are given, plus 0.77. And we're told that the overall is plus 2.7, and that means the other half equation should have an E of plus 1.63, but this is oxidation. From titanium solid to titanium 2 plus, the oxidation reaction has an E of plus. That means the reduction potential we're looking for the electrode system is the minus 1.63. Remember, we're looking for reduction potentials. Okay, this was a question in which we have the dichromate going to chromium 3 plus, the chlorine going to chloride ions, and we were supposed to form chlorine, so we said we invert that second equation. Now, what is the question? Explain in terms of electrode potentials why acidified dichromate ions react with concentrated HCl to form chlorine, even though the total E cell for that is minus 0.03. So if we add all of this, the E cell of plus 1.33 minus 1.36, the overall is a minus 0.03. This is negative. It shouldn't be feasible, but we're told that it works if we put concentrated hydrochloric acid. Why is that? Of course, if we add concentrated hydrochloric acid, that means you're adding the H plus ions, and that means that first equation will shift to the right. When the reaction goes more forward, the E of that half cell increases. So that first equation, which has a positive E, would increase a little bit, so become more positive. At the same time, you're adding chloride ions. You're adding concentrated hydrochloric acid, so you're adding chloride ions. This also would shift the equation below towards the right to form more chlorine, and that means that E will become less negative. It will be a higher value, so it will become less negative. So the overall E cell would be higher or become more positive, and that means the reaction would occur. This happens if the E cell is minus 0.0 something, so it needs just a little bit to become positive. Then shifting the equations to the right increases the E cell overall and makes it more positive. A student suggests that the ion VO2 plus may be converted into V3 plus using sodium thiosulfate with no other vanadium species being formed by reduction. Justify the use of sodium thiosulfate for this reaction by writing the relevant equations and calculating their E cell values. And of course, you have all of this in the data booklet. So what do we want? We're looking at the S4O6 going to S2O3 because we want, the question says we want to convert VO2 plus to V3 plus, and we get these E notes from the data booklet. Now, if we invert that first equation, then the E is minus 0.09. We add the other one, the overall of that E cell is plus 0.25, so that reaction is feasible. We're saying we want to suggest that the VO2 plus may be converted into V3 plus using the sodium thiosulfate with no other vanadium species being formed by reduction. So we are forming the V3 plus. If we want to go on and go to V2 plus, remember that we're reducing it. So if I have VO2 plus, I can reduce it to V3 plus. Now, will the V3 plus continue and be reduced to V2 plus? If we calculate the E cell for that, the E cell overall becomes a negative value, and that means it is not feasible, and that means the V3 plus would not react further and be reduced to V2 plus, and that is what the question is saying. This was another question where the question says 25 centimeter cubed of 0.1 mole per decimeter cubed of something, X2O5, reacts with a reducing agent, so X is reduced to a lower oxidation state. Then to oxidize it back to its original oxidation state, we reacted it again with potassium permanganate, and it needed 50 centimeter cubed of 0.02. We're given that the half equation of the permanganate, 1 mole of permanganate needs to take 5 electrons. Calculate the oxidation state of X after it has been reduced. So, we're starting with something, X2O5. We have a certain concentration and volume. In X2O5, you know that each oxygen has an oxidation state of -2, that means -10, and that means each of the X is plus 5. So we know that we're starting with X plus 5. Now, it reacted with a reducing agent and it was reduced to a certain oxidation state which we don't know. In order to determine what was the oxidation state after reduction, we reoxidize it again with the potassium permanganate. Now, the number of moles of permanganate comes out to 0.001 mole. And that means if we also have the number of moles of the X2O5. So from the information we have, the number of moles was 0.0025. X2O5, each mole has gives 2 moles of X. So that means if I have the number of moles of X2O5, number of moles of X is this number of moles. Now, comparing the manganate to the X, we found that 1 mole, if we're looking at the ratio between them, 1 mole of manganate, which gives 5 moles of electrons, reacts with 5 moles of X. And that means that the oxidation state of X changed by 1. So from plus 5, it went down by 1. So that is plus. Okay, then we need to know about hydrogen-oxygen fuel cell. Of course, we know that this involves hydrogen gas and oxygen gas. These react to form water, and this causes the transfer of electrons that cause an electric current. Of course, in here, the platinum is an electrode and it acts as a catalyst. We need to know the equations that happen in an alkaline electrolyte and in an acidic electrolyte. In both cases, the overall reaction is hydrogen plus oxygen to give water. The anode is the negative electrode, and this is where we have hydrogen loses electrons, so this is oxidation. At the cathode, it's a positive electrode. The oxygen gains electrons, so this is where reduction happens. So a question says, which is true of a hydrogen-oxygen fuel cell? Well, let's take a look at the choices. These were the equations in the alkaline electrolyte and in the acidic electrolyte, and the choices that we have: the cathode has more positive potential than the anode. Yes, the cathode is positive compared to the anode. Hydrogen is oxidized at the cathode. No, hydrogen is oxidized at the anode. Oxygen is reduced at the negative. Oxygen is reduced at the positive. The cell potential is different under alkaline or acidic conditions. No, the cell potential is the same. Which statement is correct for an alkaline hydrogen-oxygen fuel cell when compared to acidic? Please remember that for the alkaline, when compared to the acidic, the alkaline has the catalyst more efficient. Then we talked about transition metals, and we said which ones are regarded as transition metals. We said they have to be in the D block, so in that central part of the periodic table, and they have to have ions with incomplete d orbitals. So that's the definition of transition metals. D block elements in which the ions have incomplete d orbitals. We can also identify the transition metals from the successive ionization energies. Remember, we use successive ionization energies to determine if an element is in group 1 or group 2 or group 3. For example, if we look at these choices, we said if we look at A, there is a huge jump after the third ionization energy. That means that's something in group 3. If I have a huge jump after the fourth ionization energy, that is in group 4. a huge jump after the third ionization energy group 3, where we do not have a huge jump from one ionization energy to the next, that is probably a transition element. So remember, there will be no huge jumps in the successive ionization energies, then that's a transition element. How do we write the electronic configuration of transition elements? Of course, we fill the 4s before the 3d. So we have vanadium, for example, has 23 electrons, atomic number 23. We fill the 4s, and then we put 1 into each of the 3d orbitals before we start to pair them. Then when we try to form ions, we're removing electrons. We start by removing the ones in the 4s. So when filling, we fill the 4s before the 3d. But when removing, we remove from the 4s first. Now, exceptions to that are chromium and copper. Remember, we said chromium has 24 electrons, so it should be 4s2 3d4. But actually, we need just one more electron to have the 3d half filled. So for chromium, we say it is 4s1 3d5. That means the 4s and the 3d are now half filled, and that is more stable. For the copper, we need 29 electrons. That means it should be 4s2 3d9. But then I can just take one of the 4s electrons and put them into the 3d, making the 3d completely filled, so it is actually 4s1. Remember, scandium and zinc are not regarded as transition elements. We said to be a transition element, it must have incomplete d orbitals. So for scandium, for example, it has scandium 3+, in which it has an empty 3d, and zinc forms zinc 2+, in which the 3d is completely filled. So if we look at this, what is the electron configuration of the iron 2+? Remember that iron has 26 electrons, 4s2 3d. 6, if it forms 2+, then we remove the 2 electrons in the 4s. Remember, in the 3d, we fill 1 electron into each orbital before we start to pair them. What is the electron configuration of the copper species? Copper, copper +1, copper +2. Remember, copper is 29, 3d10, 4s1. So if we have, and we said that is an exception, we don't say 4s2 3d9, we say 4s1 3d10 in order to have a completely filled 3d orbital. Now copper plus, that means we're going to remove the 1 electron in the 4s, so that is a 3d10. And the copper 2+, we remove 1 electron from the 4s and the 1 electron from the 3d, so that makes it 3. This question says, which of these has the greatest number of unpaired electrons in each of its atoms? So when we draw out the electron configuration for chromium, for example, we said chromium is 24. It is 4s1 3d5. We said we do it like this so that we have half filled. That means we have 1 paired electrons in the 4s and 5 unpaired electrons in the 3d. If we do the electron configuration of iron, we get 4 unpaired electrons. Manganese has 5. Vanadium has 3, and that means the one that has the greatest number of unpaired electrons is chromium. Explain the highest stable oxidation state formed by vanadium. Remember, what is the highest oxidation state for any of the transition metals? It is when we remove all the 4s and the 3d. So for example, vanadium has 2 electrons in the 4s, 3 electrons in the 3d. If it removes the 2 in the 4s, that's plus 2. And then we remove successively each one from the 3d. That means the highest oxidation state that vanadium can have is when we remove 5 electrons, so that's plus 5. Explain in terms of electronic structure why iron 3 compounds are more stable than iron 2 compounds. You should realize that iron is 26. Now, to form iron 2 plus, I remove the 2 electrons from the 4s, and that means I have paired electrons in the 3d which repel each other. But the iron 3 plus, we're going to remove the 2 electrons in the 4s plus 1 from the 3d, so now we don't have any paired electrons that repel each other. So iron 3 is more stable because it has a half-filled 3d5, while the iron 2 has paired electrons that will repel. Then we need to know about ligands and complex formation. You should know that a ligand is a species that can donate a lone pair of electrons and form a dative bond with a central metal ion. For example, we could have chloride, ammonia, water, hydroxide ions can act as ligands. When they form dative bonds to the central metal ion, then this is called the complex. And the number of dative bonds, or the number of coordinate bonds made, that is the coordination number. So for example, this is a complex between chromium and 2 types of ligands, chloride and the diamine part. These form a total of 6 dative bonds to the chromium, so the coordination number here is 6. Remember that the overall charge on a complex ion is the sum of the charges on the central ion and the ligands. So for example, here we have copper was 2 plus. It is complex to ammonia and water. None of them have any charge on them, so the overall charge of the complex is the 2 plus. But if we have chromium, here chromium alone is a 3 plus ion. Each of the cyanide that is forming a dative bond to it, each of the cyanide has -1 on it, and that means the overall charge for that complex is 3 negatives. Copper here is a copper 2 plus. It is forming a complex with 4 chloride ions. Of course, each of them has -1, and that means the overall charge of that complex is 2 minus. So, this is a question. It says the bonding within this complex is what? So, if I have this kind of complex in which the copper is forming dative bonds with 2 water and 4 ammonia, the overall charge, of course, because the copper is 2 plus and the ammonia and water do not have any charge, so the overall charge again is 2 plus. What kind of bonds do we have? Well, within the complex, so that means inside this complex, I have water forming covalent bonds, ammonia forming covalent bonds. And then between each of these and the copper, we have dative bonds, so we have covalent and dative covalent bonds. In which species does the transition metal have the lowest oxidation number? Well, how do we know? Well, that depends on the charges on the ligands and the overall charge. So, for example, if I say copper with 2 ammonias and the overall charge is +1, remember each of the ammonia does not have any charge on it, so that means the +1 is the charge of the copper. Now, iron with 6 cyanides, we said each cyanide is -1. If I have an overall of 3 minus, that means my iron was +3. Manganese sulfate, you know that the sulfate has a charge of -2, so the manganese here must have a charge of +2. What about nickel with CO? Remember, each CO does not have a charge, so if there is no overall charge on the complex, then the nickel has an oxidation number of 0. What are the types of ligands? Where some ligands are monodentate. Monodentate means they form one dative bond to the central metal ion. So cyanide, for example, is monodentate. Ammonia is monodentate. Water and chlorides, all of these are monodentate ligands. Bidentate ligand is one in which the ligand forms two dative bonds to the central metal ion. So these are examples of bidentate ligands. Each of them form two dative bonds to the central metal ion. We also have polydentate ligands. Polydentate ligands can form many dative bonds to the central metal ion. An example is what we call EDTA. EDTA is a hexadentate, means it can make 6 dative bonds to a central metal ion. So, if we have this question in aqueous solution, iron 2 exists in this form. Explain how water acts as a monodentate ligand. Remember, we said a ligand is one that has lone pair of electrons that is used to form a dative bond. So, water has lone pair of electrons on oxygen that is used to form a dative bond to the central metal ion. Which complex contains a bidentate ligand? Again, if you look at A is this kind of ligand. This has 3 nitrogens. Each of them can form a dative bond, so this is actually a tridentate ligand. Ammonia and water are all monodentate. This one that has 2 nitrogens on it, this is a bidentate ligand. We said EDTA is hexadentate, so the bidentate is that choice in C. Copper 2 ions form a complex with something called 1,2-diaminoethane. That is the one that we were talking about, that has 2 nitrogens. Each of them can form a dative bond, so it's a bidentate. And we're told that it forms this formula. That means the copper is bonded to 3 of them, but each of them can form 2 dative bonds. So the type of the ligand is bidentate, but the coordination number, we have a total of 6 dative bonds made to the copper ion in the center. Structure of the complexes, this depends on the number of ligands. So if we have 2 ligands, that means we have 2 shared pair of electrons to the central metal ion, and that means it should be a linear structure with bond angle 180. And if we say why is that, it's for minimum repulsion between the shared pair of electrons. So if we say explain the shape of the silver ammonia complex, we said this has 2 ligands, so they have to be as far away from each other as possible. It is linear with bond angle 180. This is for minimum repulsion between the 2 bonding pairs of electrons. If we have 6 ligands, then it is octahedral for the same reason. So we have all of these 6 ligands, octahedral structure. And if we say again, explain the shape, this is octahedral for minimum repulsion between the 6 shared pairs of electrons. If I have 4 ligands, then that would be a tetrahedral structure, again to spread them away as much as possible. If we have 4, they could be, we said they have 4, we could be tetrahedral. So if we're doing with chloride ions, they are tetrahedral. but sometimes they are square planar. For example, the platinum with 2 chlorides and 2 ammonia, this is called platine. We can have 2 forms of it, a cis and a trans, and the importance of this is that the cis is used as anti-cancer drug. And you should know that this is because it binds to the DNA in the cancer cells. Remember, DNA has what we call nitrogen bases. The nitrogen bases have nitrogen with lone pair of electrons that can be used to displace the chloride ions on the platinum complex. So platinum, that when it is cis, the 2 chlorides are near to each other, so we can form 2 bonds with the nitrogen bases on the DNA. This sort of traps the DNA, it cannot replicate, and the cells die. The lone pair of electrons on the nitrogen bases, this is what is used to form the dative bonds with the platinum, and the trans cannot do that because the trans has the chloride ions on opposite side of the platinum. So if one of the chlorides is displaced, the DNA or the nitrogen base on the DNA cannot reach the other side and displace the other chloride. So the trans cannot form 2 bonds with the DNA, it forms only 1, and that doesn't affect the DNA much, but the cis forms 2 bonds to the DNA, and that prevents it from replication. Which complex is tetrahedral? Again, if we look at this, remember we said the platinum forms square planar, whether it's cis or trans, so it's not tetrahedral. First of all, to be tetrahedral, we must have 4 ligands, so B and C are not. These are forming 6, 4 water and 2 OHs, so that's octahedral. 4 ammonia and 2 water, that's octahedral. Cobalt with 4 chlorides, we said this is the one that is tetrahedral structure. Which transition metal complex is commonly used as a treatment for cancer? Again, remember it is the cis platine, in which the platinum has the 2 chlorides next to each other. Complexes could have stereoisomerism, in which we have cis and trans, because the complexes are trapped in a specific configuration, so we can put them either next to each other. So for example, the one below, I can put the nitrogens next to each other on the same side of the copper or on opposite sides of the copper, so this is referred to as cis and trans. We can also have optical isomerism, in which we have mirror images that are not superimposable on each other, so these are optical isomers. So for example, the question says, explain why the tetrahedral complex shown exists as 2 optical isomers. This is because, of course, the cobalt has 4 different ligands attached to it, so it has 2 non-superimposable mirror images. Most of the transition metal complexes have colors, and this is because originally all the 5d orbitals should have the same energy. So when we're writing the electron configuration, we say that all the 5d orbitals have the same energy, but when it forms complexes, the repulsion between the ligand and the central metal ion causes the d orbitals to split, so that 2 of them have higher energy than the other 3. And that means when light shines on the solution of this complex, an electron in the lower energy level can absorb energy and jump to the slightly higher d orbital. The rest of the light is transmitted, so we see that as the color of the complex. So in order to have a color, first of all, the d orbitals must be incomplete. If we have complete d orbitals, then this kind of transition that we're talking about cannot occur. So if we're talking, for example, about S block elements, we know that S block elements, the compounds are not colored. This is because the energy gap is too large when we're talking about jumping from an S to a P, for example, and so on. This is a very large energy. It doesn't happen, so the compound is not colored. So we're talking about the d orbitals, because when we have ligands, the d orbitals split a little bit, with one having higher energy than the other. If we have a complex like Ag plus 1, we know that Ag is 5s1 4d10. So when it forms Ag plus 1, we're removing the electron from the 5s. That means it has a filled d sublevel. If we have a filled d sublevel, then no transition happens and the complex does not have a color. Which complex ion is colorless? Remember, first of all, to be colored in the first place, it must have a transition element. So if it has aluminium, which is in group 3, it cannot be colored. The others have colors, and we will talk about that. The copper water complex is copper 2 plus is blue, the iron 3 plus is brown, and the nickel 2 plus is green. If we say the diamine copper 1 ions are not colored, again, why are they not colored? Because the copper alone is 4s1 3d10. Now, if I form copper plus 1, I removed the 1 electron from the 4s, so the 3d is filled. And we said if the 3d is filled, this transition from lower d orbitals to higher d orbitals does not happen. But copper 2 plus is colored. This is because we're going to remove an extra electron from the 3d. That means now the 3d is incomplete, so the copper 2 plus would have a color, while copper 1 does not, because dd transitions are not possible since the d orbitals are fully occupied. Again, if he says explain why a compound T, this was compound T in the question, is colored, while compound V, this was compound V, and we're told that V is colorless. Explain, we said again, in order to have a color, we must have incomplete d orbitals so that the ones in the lower orbitals can gain energy and jump to a higher energy level. So if we're talking about copper, we said copper alone is 29, 3d10 for s1. If I say copper plus 1, which is the one in V, copper plus 1, we remove the electron from the 4s, so the 3d is complete. While the copper 2 plus, we're going to remove another electron from the 3d, so we said the 3d is incomplete. So a copper 2 complex would have a color. The copper 2 plus has the 3d incomplete. So when light shines on the solution, an electron absorbs an amount of energy, jumps to the d orbital at the higher energy level. The rest of the visible is transmitted and a color is observed. But copper 1, the 3d are filled, so no electron transition happens, so no color is observed. Okay, we could have substitution of ligands, and you should know that when we have monodentate ligands, I substitute it with a bidentate. That's a more stable complex. If I substitute it with a hexadentate, that is even more stable because it will have a more positive delta S system. So in this question, we're told nickel 2 complex ions are formed by addition of complexing agents to nickel 2 ions. On formation, which of these would lead to the most positive increase in delta S system? We said if we substituted so that we, instead of monodentate, we have hexadentate, then that is much better. So the nickel with the EDTA would be the most stable, so most positive increase in delta S. Okay, we'll stop here in this part of the review, and we will continue talking about the rest of the topics in the next part.